right?
Yes.
All right, so we have, so we're going to start with this, and you're hopefully just going to write this so much that you remember it, but it will always be given.
Insulated, so Q cancels. Steady, DE, Z cancels.
I'm still writing.
Oh, sorry.
Okay, so yeah, it's well insulated. So there's no heat transfer in the control volume. We have speeds. It's steady state. So, so those are just m dots, and this is equal to 0. A nozzle is always rigid, so there's not going to be any work in the control volume.
Potential energy 0.
Yep, so those two cancel out. And so, okay, it's steam. So, and since everything's canceled that doesn't have an m dot in front of it, we can divide everything by m dot. And so we just get that HE plus VE squared over 2 is equal to HI plus VI squared over 2. And we are given pressure and temperature, which should, make you think like, okay, this is steam. Like we have tables for that, and we have all the information we need to look stuff up in tables. The velocities are given. So let's see. So we have. Do you have the looked up values there?
Maybe.
Do the tables have it in those units? I hope so. We don't have to convert.
I had at 280 degrees Celsius and 2 H 2976.4 kilojoules.
Okay, wait. Okay, let's see what we
get all that.
let me look at the tables and see what we have. We might have the tables in those units. What?
I feel like the tables always trip me up.
Oh, yeah. So basically, we're going to have to do kind of like a reverse lookup for this, So we're going to calculate the final enthalpy, and then we're going to have to find the spot in that in the tables where. Okay, so we have water, not at saturation. It says it's steam, right? And that is all in SI units. Do we have anything else? No, not in that one. Let's look at the complete. Water, A5, no, A6, Okay, so that's SI units. Eh, that sucks. So we have to convert all that. Um, okay. All right. So let's see. 300 pounds per square inch. Oh, that's PSI. 300 PSI to bar. So 20.68 bar.
So is that a typo? Pounds per, instead of PSI, you pounds per foot per square inch?
Pounds per. Oh, that's that F is for force because apparently people sometimes use pounds as mass. So that's just saying, sort of specifying that it's force. And then 600 Fahrenheit. $315.6. We'll worry about those in a second. And then 40 PSI. Yeah. So 2.76 bar. And
Do you need velocity in meters squared?
yes. So what's 100?
30.48 is what I got.
30.48.
Hopefully. 1800 is 548.64.
Okay. And so the first thing we want to do is we want to use the tables to look up steam. We want to find the enthalpy. So at state 1, we have a P1 of 20.68. And a temperature 1 of 315.6 Celsius. And we're going to have to do this as a double interpolation, a two-step interpolation. Let's just, instead of doing the interpolation, let's just use the closest values. You know what I mean? Just to not do that right now. So hopefully there's something at like 20 and 300 or something. So you would have to interpolate this, and it should give you something like a specific enthalpy of let's see, 20 bar. So 20 bar, 320 So specific enthalpy is the third category. So somewhere around 3069.5.
I think I got 3059.
Okay. With the interpolation?
I think so.
Okay. That's great. So I'm just going to call it this. And that's times 10 to the third because it's kilojoules. And so we have that HE plus 1800 squared over 2 is equal to 3060 times 10 to the third. Plus 30.48 squared over 2. And that says that the enthalpy at the exit
Why is it 1800 and not meter per second?
Yeah, you're right. It's the meters per second. 548.
Yeah.
So 2.91 times 10 to the 6. And that is joules per kilogram. And now we're going to go to the table again at, say, 3 bar or whatever's, you would have to do this as an interpolation, and it would be a super pain, but we're basically doing like a reverse lookup, So we know that the pressure is 2.76. So let's call it 3. And we're looking for a value of 2.91 times 10 to the 6. So in here somewhere between 200 and 240 degrees Celsius. Call it 220.
It was close.
Anybody have any questions about that process?
Just how did you get the work?
How did I get what?
The work.
Oh, so a nozzle is always a rigid device. There aren't. Yeah, right. And right, exactly. Any other questions? Any other homework problems you want to see? Okay, so we are on, I think, we were going to do an example problem for a turbine, and then we still have compressors and pumps to talk about. So let's say that, let's say we have steam at steady state. This is an example problem. With a mass flow rate of 1.2 kilograms per second. And at the inlet, we know that the pressure is 60 bar. The temperature at the inlet is 400 degrees Celsius. The speed at the inlet is 10 meters per second. And then at the exit, the pressure is 0.1 bar. The speed is 30 meters per second. And we have a quality of 0.9. So it's a superheated vapor at the inlet. At the exit, it's a saturated mixture of liquid and vapor. And what we want to do is first use the standard turbine assumptions. So the simplified ones I gave last time. To find the power generated. Second, we want to figure out what's the error in this case in assuming that the change in kinetic energy is 0. So you asked about that last time. Like, that's weird that we don't worry about the change in speed of the material as it goes through the turbine. So here we have the speed, so let's see how much of a difference it makes. And then third, if we remove the assumption of no heat transfer, so in other words, we're going to remove the assumption that Q dot is equal to 0, and we assume 100 kilowatts of power is generated. What's the rate of heat that's lost? Okay, so we're going to start out with the standard assumptions that we made last time. So that is that the rate of work generated is equal to the mass flow rate times the quantity HI minus HE. From the steam table, we are given a pressure and a temperature, so we can look this up. The specific enthalpy at the inlet is 3658.4 times 10 to the third joules per kilogram. And then at the exit, we're told the quality here. So we know it's saturated. The fact that it gives you a quality says we know it's saturated. So we can use a saturation table, which means that a pressure is enough to look stuff up. Okay, so from the saturation table, we know that, so think about how you'd have to look this up in the saturation table. We have a pressure. That's going to let us look up a specific enthalpy for a saturated liquid and a specific enthalpy for a saturated vapor. Those are two different values. And then we're going to have to use the quality to come up with our mixture's specific enthalpy. Okay, so for a liquid, it gives 191.83 times 10 to the third joules per kilogram. And for a vapor, it gives 2584.7 times 10 to the 3 joules per kilogram.
And these are from the water tables?
Yeah.
So anytime it says steam, you can just that's water.
Right. That's right. And so H at the exit is 0.9 times the 1 for the vapor plus 0.1 times the 1 for the liquid. And that is 2345.4 times 10 to the third joules per kilogram. And now we have everything we need to plug it into this equation. So the power generated, W dot, is equal to, we had a mass flow rate of 1.2 times the quantity, inlet enthalpy, 3658.4 times 10 to the third, minus exit enthalpy, 2345.4 times 10 to the third. And we get a value of 1575.6 times 10 to the third joules per kilogram. And this is actually, it's not per kilogram, it's, this is an extensive power, and power means it's in watts, so this is in watts.
Because
Same
you
thing as,
multiply it by the mass flow rate.
yeah, that's right. Okay, so now we're gonna, for part B, we're also given these speeds, so now we can do it again and see what our power generated calculation is, putting those speeds in, and we can see what kind of error we had. So I'm going to go back to the full form. It's in steady state, so I'm going to just start canceling this stuff out right at the start. So this is m dot, because it's steady state, times the quantity hi, plus this time we're keeping the speed terms in. We're still leaving out the potential energy terms. We're still, for part B, assuming that there's no heat transfer. And so we can rearrange this as W dot in the control volume is equal to M dot times the quantity HI minus HE plus VI squared over 2 minus VE squared over 2. And all we're doing is plugging in the these additional values. So, I could write this as m dot times the quantity hi minus he plus m dot times vi squared over 2 minus ve squared over 2, because this is the stuff we had before. And so this is 1575.6 times 10 to the third plus 1.2 times,
I thought the 1575 was the work.
that was the work that was the rate of work that we got from assuming that the speed didn't change, neglecting the kinetic energy stuff. And so what this number is just m dot times the difference in the specific enthalpies. Okay.
So that first term is just the answer we already found.
That's right. That's why I separated it out that way, just so I could use the value we already had instead of punching everything in again, So VI, let's see. So we got a 10 and a 30. So 10 squared over 2 minus 30 squared over 2. So we got 50 minus 450 times 1.2. And so this term is negative 480 watts. And so that's the difference, basically, is we were off by 480 watts. Well, I mean, that's negative 0.48 times 10 to the third watts, compared to this. So the answer is, if that's sort of a standard change in the speed that you can expect, you can see why people tend to ignore that. It just doesn't account for very much. Any questions about that?
Is that more so true if it's like a high enthalpy system? Like wind turbines, you wouldn't want to just record kinetic energy. Is more energy from like a wind turbine coming from kinetic energy, or is that enthalpy as well, like in just standard atmosphere?
Let me think. So the turbines that we're going to do calculations for, you have a pretty good measure of where the material is. Like I think it would be hard to use this control volume approach for a wind turbine, because it seems like you wouldn't have a very good idea of what the volume is that you're looking at. Yeah. But I think the answer is you still would have a very high pressure on the inlet side of a wind turbine and a very low pressure on the exit side of a wind turbine. And that would mean that the enthalpy is much bigger on the inlet side than the exit side. I don't know. I would guess it's sort of similar. I mean, I think when you just look at I think really it's just a matter of we were talking last time about how thermal energies in our experience are big compared to kinetic energies and potential energies and electrical energies. And I think just the speeds that you're dealing with are small enough compared to regular enthalpies. Just regular atmospheric enthalpy is a big amount of energy, whereas wind moving at 5 meters per second or whatever, it just isn't very much kinetic energy. I think that's the thing.
So is that just like the number of atoms colliding just tends to be higher from the random motions than the average of their motion over time?
That's an interesting way to think about it. I guess that's probably right. Yeah, right.
Okay.
They're vibrating more than they're deciding on a direction.
Slowly traveling in direction.
Yeah.
Okay. Got it.
Okay, and then C. So we figured out basically that speed doesn't matter too much. And so I'm going to leave that out in part C, although you could put it in also. But what we're supposed to do for part C is now, assuming that you measure the power generated and it's 1,000 kilowatts, then the only place that energy can be going is the heat. So how much are we losing in heat? Well, I guess the answer is going to be somewhere around 1,500 minus 1,000. You know, it's going to. But let's just go through it again. So it's steady state. And so our dE dt is 0. And this time that's equal to the rate of heat. It's actually heat coming in. So if we're losing heat, we're expecting this to be negative. Minus W dot, and we're assuming that this is 1,000 times 10 to the third. And then plus, I'm going to just go back to 1575.6 times 10 to the third. And so we get 0 is equal to Q dot minus 1,000 times 10 to the third plus 1575.6 times 10 to the third. And so Q dot is equal to negative 575.6 times 10 to the third watts. Any questions about that? And then the last two types of devices are compressors and pumps. Compressors are when we're talking about gas or vapor. Pumps are when we're talking about liquid. Compressors are only used to increase the pressure at the exit. Pumps can be used two ways. So first, it can be used the same way as a compressor to increase the pressure at the exit. Or a second way is to increase the height of the liquid at the exit. And so I'm going to do first come up with a simplified form of the control volume equation where I'm increasing the pressure at the exit, and this works for both of them. And then I'll do a separate one for a pump where you're just trying to move liquid from a lower height to a higher height. So the first simplification is for compressors and pumps increasing the pressure. At the exit. And the assumptions that we're going to make are first, steady state. Second, the change in potential energy from the inlet to the exit is 0. Third, that it's happening quickly, so there's no heat transfer from the control volume. And fourth, that we're not worried about a change in speed. So we're going to assume that the change in kinetic energy is 0. W dot is not going to be 0. This time that W dot is referring to like the electric power, or mechanically, if you're doing it, the rotating shafts coming in to create this difference in pressure. Okay, so it's like the opposite of a turbine. A turbine is outputting power. This is inputting power. So dEdt is equal to Q dot minus W dot plus its steady state, so I'm just going to call these M dots right from the start, times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity H exit plus V exit squared over 2 plus GZE. This goes away. There's no heat transfer. The kinetic energies cancel. The potential energies cancel. And we get an equation. W dot for the control volume is equal to M dot times the quantity HI minus HE. Okay, so there's the simplified form. And the first thing to notice is we just did this example. There's the simplified form for the turbine. So this is exactly the same form as the simplified turbine. The difference is both sides of the equation are negative here. In a turbine, both sides of the equation are positive. So if you had perfect efficiency, you could hook up a turbine and a compressor and run it forever, you know, but it doesn't work that way in practice. And then what do we have? So yeah, let's do it so this could represent a compressor or a pump where your goal is to increase the pressure at the exit. The second simplification is just going to be for pumps. where we're trying to increase the height. At the exit. And the assumptions we're going to make here are steady state. Again, I mean, everything is, we're going to assume steady state all the time, because if your devices don't eventually get to steady state, then they're going to blow up, you know, something's going to go wrong. So everything needs to get to steady state at some point. No heat transfer. No important change in kinetic energy. And this time, we're going to assume that the pressure is the same at the inlet and outlet, inlet and exit. Because, for example, you know, if you're talking about, if you imagine, you know, pumping water out of a hot tub or something, the pressure is atmospheric pressure on this side where you're getting the water, and it's atmospheric pressure over here where you're pumping it into the drain or whatever. So the pressure is the same. And so that means that there's no change in enthalpy. I guess really I should say the pressure, but also the temperature. I mean, you're just assuming the atmospheric conditions are the same at the inlet and exit. So there's no change in enthalpy. Okay, so this is the last time we have to sit here and go through this full equation together, but d dt for the control volume is equal to q dot minus w dot plus, because it's steady state, just m dot times the quantity hi plus vi squared over 2 plus gzi minus m dot times the quantity he plus ve squared over 2 plus gze. The EDT goes away. There's no heat transfer. This is still the work coming in, the electrical work coming in. The enthalpy at the inlet and exit are the same. The kinetic energy is the same. And so we get a simplified form that says W dot for the control volume is equal to M dot times the quantity GZI minus GZE. And so this exchanges power, almost always electrical, for potential energy. And again, both sides of this equation are negative. Any questions about that? Okay, that's all.